Well, welcome everybody. My name is Roger Gurmanson. Those of you who've been here before have seen me many, many times. I'm going to talk about geometric computation. This is a project that's pretty comprehensive in scope. It's not in a finished state, so it's not part of the pre-release as of yet. And you'll see that this is a little bit more fluid than some of the other projects that we sometimes present, certainly from the algorithm side. We wanted to showcase this to you guys and get some feedback on where we're at now and suggestions and so on. So first of all, there are several people involved, and I'm going to point to you. We have many complementary talks, and we're going to talk about these different areas. And so one thing is that here's how you can identify team members. So seek them out and bug them, and here are the additional talks. So in this afternoon, we have a 1-hour talk that covers the different types of regions. So region is a point set. That's the kind of objects that we compute with. We have solvers, or solving, computing with regions. This is about defining and different ways of defining and modeling. This is about computing with them. And then there's additional in-depth coverage of computing. All right, so let's get started. Let's start at the high level. So I'm going to keep most of my regions fairly simple. So one thing is that, so what is a region? A region is a point set, and over the reals in our case. And one thing that we can do is, the question is, what can you do with those regions in Mathematica? So let's start there. Let's start at the superfunctions or the solver functions in Mathematica. One thing, you've seen some of this that Stephen showed, some of this already yesterday, is that we can give any region as an argument to one of our plot functions. And the way we indicate that your variables should be in that region is that you just say that the point, x, y, are element of region, and that will do the plot for you, as you can see here. This works with just about any of our visualization functions that plot functions and so on, and we might generalize that to our data visualization functions as well. So this becomes very convenient. This allows you to visualize, for instance, integration, optimization, all kinds of problems that are typically defined over some region or constrained to be over some region. What about integration? It's another staple of Mathematica. So we can do, like in this case, same syntax you'll see being used all the time. And in some cases, for these regions, we can keep parameters around and we get conditions on them. For a concrete parameter, of course, it gets something concrete, and we can keep more things around as parameters. We can numerically integrate the same thing. It uses a different set of algorithms to do it, and it's the same paradigm that we've done with symbolic solvers, numeric solvers. So we have to keep symbols around in regions if we're ever going to be able to compute exact results and so on. For many things, you will have to discretize your region and do an approximate algorithm, just as we have for other kinds of computing in Mathematica. So here it defines...
What are the carets there for? It looks like there's something left out, or is it just
which caret?
red marks?
Oh, that means that the syntax highlighting is not installed, because it's derived from the documentation, and the documentation, we don't make it part of the main line of Mathematica yet, so the syntax highlighting can't pick it up. Though this is at the small end of things that when you work in a branch. All right, so this defines a triangle, from the origin to 1, 0, and I just want to integrate some kind of function over that region. Okay. Sorry about that. So, but here's an example of how we use plots. So this is in fact, the function I want to, integrate, over that region. We can do, for symbolic regions, we can work in any number of dimensions. So here is, for instance, a five-dimensional ball. And you can see that we can integrate. I mean, it doesn't have to be, that could be, anything. Or numerically, in this case. So let's. Now, one thing that is not in these basic examples, which is, if we take something that is a curve, like a circle, that means that I'm integrating over a curve in 2D. So integrate will automatically change its measure to, in fact, do a curve integral. Okay, so if that was a surface, it would do a surface integral. So that should be the formula that you recognize for the length, for the circumference of the circle. Same thing for numerically integrating, or along a line. We can extend this. You'll see this, a little bit farther on, but this was sort of an integration problem. But we can, in fact, include this type of syntax as another type of equation or inequality. So here's a probability that ultimately becomes, an integration problem. Yeah.
It's a line integral you just did, right? Integrate 1 as xy travels around the circle.
Yeah.
Aren't there many different definitions? There's tangential form and normal form. So you're saying it's tangential, which is sort of, I guess,
No, the measure, when you're going to integrate over a surface is this gram determinant, right?
It's my mistake. Yeah.
Okay.
Yeah, my mistake, sorry.
Right. Normally it's only defined for sort of parametric form. We just automate the whole thing for you. Okay? And I'm going to explain more things about how these special regions that I'm using now work when we've seen a little bit more. But it's interesting that we can, in fact, generalize this notion to make it part of equations and so on. And so, okay. So what about next step? Okay, solving partial differential equations over regions. So here is, a Laplacian, which we introduced in Mathematica 9. We give a condition, Dirichlet condition, which means I'm setting that function equal to this function, sine 5xy. And true here, normally I can have a condition here. So let me just do this example first, make sure things work correctly. Okay, great. So I'm solving this Laplacian equation with this Dirichlet boundary condition over a disk, or any region, really. And what it means is that all along the boundary, I have this outer boundary, I have this condition. Let's say that I restricted that to say, oh, okay, let's for x greater than, 0. Now, I would only have that boundary condition over here, and otherwise it will use a default boundary condition, which is 0. And you can have any number of them. You can have Neumann conditions. Go to Oliver's talk this afternoon, and we'll talk about systems of PDEs and all the different conditions, that's involved. I'm not going to drill into that super deep in this talk. Okay. Another thing we can do, another area that makes heavy use of regions, is an optimization. The standard way that we represent regions for optimization is with implicit forms, inequalities. So we can use what you saw me use for the probability example to include, region constraints in optimization problems. Okay, so here is, I want to optimize this thing over a disk, keeping it simple. I can keep on adding here, so I could add sort of x greater than y. That didn't have any effect. Let's do it the other way. Okay. What about, so then we can solve, you've already seen sort of along the lines that we can solve optimization problems, we can solve equations and inequalities. We add them in like this. Okay? So that if you want a sample point in a region, you can use, for instance, find instance to find a sample point in a region. Okay, so here is an example of a linear equation. and another linear equation, but it's camouflaged, using the line primitive. Let's say I put something else there, like a circle. And now I get two solutions. All right. So at that level, I think it's incredibly easy to use, given that you have constructed a region of some kind. Now, let's talk about some of the special properties that are defined for regions. So this, we have one group of properties have to do with dimensions. So all of the regions in Mathematica are embedded in some space. They live in Rn for some n. So that's the embedding dimension. Now, the actual point set also has a dimension, and that's what's called region dimension here. So if we look here at some examples, we've embedded them in 2D. So a point has dimension 0, curve dimension 1, and a solid or a region like this has dimension 2. Same thing for 3, the same geometric dimension, but it also has geometric dimension 3 for a solid in 3D. Okay. So here's an example. So a circle has, geometric dimension 1, but embedding dimension 2. A cuboid has geometric dimension 3 and embedding dimension 3. So we've documented this. You'll find additional documentation for each one of the graphics primitives that can also be used as geometric primitives that characterize what they are. Because it's a little bit unclear in our graphic system. Is a cuboid just a shell, or is it a solid? So we say that geometrically this is interpreted as a solid. Okay, so that's documented for each and every one of them. Another thing that's important is to know if a point is a member of a region. Sometimes it's very easy to test that, but I can't tell you how many questions we've had. Can I test for, a point is in a polygon, which is sort of almost the simplest of all possible membership problems, but it's now going to be trivial. So we have this element notation, which you've already seen me use for solvers. We can't let that sort of auto-evaluate when you have symbolic entries here, because we need to use that to assert membership. So remember, we use that for plot, integrate, and all of these things. If I gave numbers here and things were all numeric, it would answer true, false, okay? So we've already seen that we can use that as arguments to other things. Now, we have another function, region element, which is like element, except it actually does produce a condition that that guarantees membership. So, and also what I can do is I can have sort of a one argument form of this, in which case you will get an element function, a function that you can apply repeatedly fast. This is particularly useful for these big mesh objects where you want sort of some fast membership testing. And, right. Next up, we have moment problems or moment properties. So so a lot of these properties are not unlike other objects that we have in Mathematica, like distributions and processes and so on. There's certain things we know, like the mean of a distribution or the variance or something. Well, those are integration properties, and these guys are also, or moment integration properties, and these ones are too. So the measure, the definition, given that you know how to integrate over a region, are truly trivial. So the measure is just the length, the area, the volume, and so on, of the maximal dimension component. The centroid is a measure of centrality. Center of gravity is another name for it. Okay, so here are some examples. Measure have different names in different dimensions. If it's zero-dimensional, we usually call that measure count. If it's 1, it's length. If it's 2D, we call it area, and if it's 3D, we call it volume. And then I'm out of names. So we'll probably introduce these standard names like area, length, and so on as well. Just, they just will only work for the appropriate dimensions. Oops, I had examples. Okay. Now we've made a lot of these things work very sort of quickly. Okay, so in general, it needs to call a solver and do things. But for special regions, we can make sure that it works very efficiently. We typically derive and have special algorithms for that. So these are 2D regions. Here's a 3D region. Sometimes we can give closed form formulas. You know, sometimes they're really trivial, sometimes a little bit less so. Most of the time, they're horrible. Okay, most of the time. I mean, if you have any generality of regions, they'll fill your notebook. Okay, so unless it's sort of numericalized and stuff like that. We have, you know, we have n-dimensional boxes, so some of these things become very, very simple. You know, high-dimensional balls and ellipsoids and so on. And we can also sort of test, you know, that this should in fact, you know, be exactly the same result as we get by integrating it. Right? So if I did that, just took I just took the same, hopefully we'll get the same thing. Almost. I mean, for the regions, for the assumptions on the parameters, it's exactly the same thing. Okay, centroid. Again, remember its definition. You know, so for convex regions, it's exactly what you think. You know, once we go to sort of non-convex regions and so on, the centroid may not be in the region itself at all. Okay, here are some cases which you should all, you know, kind of recognize. And there are higher moments too. So the next higher moment, and perhaps someone knows in this audience, it's usually called inertia. Does someone know a more geometric name? It's basically like a covariance just over a region. But does someone know sort of a non-physics name for that? A more geometric name for the second moment? No?
Metric tensor?
Well, that will scare off all of our high schoolers very quickly. We have this debate in-house, you know, of... Okay. So really, at this level that I'm talking now, I think you, as a high schooler and so on, you can certainly use this, I think. Distance properties. Okay, so Bridgend distance is just the minimum distance from a point to a region. Nearest is the nearest point. You know, so this is like, this is min value and arg min. Signed region distance is incredibly useful when you do numerical computations. So it's the distance. If you have a point that's outside the region, it's the distance. If you're inside the region, it's the distance to the complement of the region, but with negative sign. So that means you get a sign change for region distance, which makes it very useful for numerics. Okay, so these are iso distance curves. So the blue here is sort of a region, and you can see various iso distance curves. So it's a way to sort of globally understand what distance means. These are simple shapes, so it's easy to kind of see what they look like. So here's the region distance to a disk. And you know, if we plot that, we'll see that the distance is 0 when I'm in the region, and then it sort of grows outside of that. We do the same thing with sign distance. Now we get iso curves also inside the region. These are negative distances inside the region. Okay, so these are of primary value only for full dimensional regions, regions that have the same dimension as the embedding space. Okay, so if I get sign distance, it looks like that. And if we compare to that other picture, you can see it doesn't go to 0 here in the middle. It continues into the negative. These things are you know, useful for lots of things that have to do with... so here's an example, which unfortunately, that looks very bright here. Okay, but so here is, I'm looking, notice here, I have a piece of code here that says if the distance is negative, green, which means I'm in the region. if distance is positive red, I'm outside the region. So I pick a region here, happens to be France, and you can see, right? Okay, nearest. This is a visualization. So with the blue here is the region, and I just put up, I can't remember, maybe 50 points or 100 points around here in a circle, and I draw a line to the nearest point. So this is a kind of a way to visualize or globally understand this. You know, so things you see here with things with corners, but it gets really interesting when you have sort of a non-convex region, where you get these, you know, it's still simple. It doesn't sort of, you know, and these are the same thing for 3D. Okay, so again, if you give it with only one argument, it will give you a nearest function. Okay, like distance function, and so on. So for fast computations on complex regions, that's really, really useful. Okay, so I do kind of the same thing. I just draw, you know, the blue is the point that I'm indicating here, and red is the nearest point, you know, and so this is, and here you can see this interesting phenomena, right, when we hear boom. Okay, your intuition is usually not, you know, once you've seen it, you know it, that this is something to worry about, but. Okay, so that is that's the special properties. These are things that are defined for every region that we define. Okay, so now let's see, what are regions. One group of regions, which are the only ones that I've used so far, are we call special regions. These are things that have names that you're familiar with. They have a few parameters to define them. And so if we look in 2D, there are things that you're familiar with. We've added a few new ones. So we're starting to have now these infinite primitives. You know, so this is a ray or a half line. This line is you know, starting somewhere, continuing infinitely far into sort of a direction, or doubly infinite line. There's a few more. We've added a whole, at sort of an internal request. Apparently in the American system, we give names to all the triangles that have, you know, if they're given by side, side, side. So we have 4 of these primitives: side, side, side triangle, SSS triangle, and SSA triangle, ASA triangle, which is just different ways of parameterizing a triangle or a simplex. But it's now a primitive. 3D, we've added a bunch of volume primitives. So you have, again, you have these half lines, infinite lines. You have a half plane. You have an infinite plane. But we've also added additional volume primitives, like a tetrahedron, hexahedron, prism. And there's a few more that I forgot to put on here, like ellipsoid, a general ellipsoid defined by a positive definite matrix, or a ball defined by n+1 points, and so on, that also work in any number of dimensions. Right, so these are the ones that generalize to dimension n. So let's look at some, just some simple examples, although we've used some of these already. We've seen this, we can plot over a region. What about if I'm integrating over a region, something else? So one thing that we can do for these special regions, we can derive even more sort of efficient code. So for some of these classes, like balls and ellipsoids and simplices and so on, we have super fast polynomial integration code. So if you happen to want to integrate over balls in dimension 100, some horrible polynomial, it will still be in the milliseconds. So it should work fine. Otherwise, it will have to do something fairly sophisticated using semi-algebraic sets and so on, and it will be very, very hard. So here's an example of that. Okay, so here's integrating over some ellipsoid, and you can't see that, but it's, well, I have no idea. And generally, we can tune sort of performance like that. You know, if it's possible, we can, yes, in the less than milliseconds. Same thing for simplices and so on. Cylinders. Okay, so now I'm using, this is optimizing over a cylinder, again, computing some probability here over a ball. Oh, it's still working. Okay, the n-dimensional ones. Right, so this is just the volumes over a standard simplex, like the unit triangle, with sort of points out for along each axis and the origin, or integrating over them, and so on. Okay, these are special regions. Okay, so now I'm transitioning into general regions. These are much more flexible regions. So generally speaking, these special regions can be translated into all the types of region that I'm now about to describe. But if you can stick to that more special case, you can often do things much more efficiently. Okay, so an implicit region is something that you've been used to in Mathematica, which is to give type of input that you can give to region plot and contour plot and so on. And so these are known by various names like level sets and R sets and contour regions. These ones we can work with symbolic computation. The things for which it works, we can guarantee that it will work, or for semi-algebraic sets, and then a little bit extended beyond that. Works in any number dimension, works happily with unbounded regions. Okay. So here's an example. So here's an ellipsoid, as you might know it. And, I can continue to use that type of region just as I used the region so far. This is a curve integral. So this is the length of that curve that we saw. Or an ellipsoidal annulus. Again, we can just keep on working with that like everything else. The other thing that they can do is to represent mixed dimension things. So generally speaking, all the examples you've seen up until now have been sort of one dimension only, but there's nothing that prevents our regions from having, like graphics, having multiple kinds of dimensions, multiple geometric dimensions in them. So here's an example of that. Now if I integrate over that region, it will pick out the maximal dimensional component, and that's the measure, and that's what it will integrate over. Everything else is measure 0 from that point of view. When we optimize, on the other hand, we use we use everything. We use the lower dimensional pieces as well, because that's what the natural sort of minimum distance is. Here's some 3D examples. This one stopped working this morning. But this would be a line. It's an intersection of, let's say, two surfaces here. This would be a line, but that should work in the future. Here's what we think of as a normal surface. So it's a 2D thing embedded in 3D. But we can integrate. This is the area of that surface. It was bounded. Look, I put in these bounds. So if you see that normally auto-evaluates to include the bounds. Okay. Here's a volume region. And again, I'm just using one solver function sort of to test to see that we can actually do some computations on it. And right. Another group is again, it's a formula region. It's a parametric region. So so you have some number of parametric functions, and you have some number of parameters. The other case is that we want to constrain the parameters. This gives you basically a subregion of Rn over which I'm mapping. Okay. Again, it works in any number of dimensions, can represent unbounded regions, and so on. So here's, let's do the same ellipse, but using a different kind of representation. And should get the same result. Or Again, a different kind of representation for the same region. Again, if you look at how this auto-evaluate, it will put in these conditions here. This was the form that we documented. And should be able to compute over that. Let's go to 3D. So here's a curve. Again, if I put that in, you see it put in the condition there. But again, I can do an integral over that curve, which is the length of that curve, or a surface. We'll see, it'll put in the conditions. And can figure out what the area is of that surface. Eventually. Oh, we did, okay. The volume. So it has 3 parameters that make it up. Again, can integrate over that. Okay, so both of these are fairly general kinds of things, and that allows us to capture all the sort of classical ways of defining, curves, surfaces, volumes, and so on, that you might be derived from some other means in Mathematica. Let's talk about mesh regions. So mesh regions, they're basically geometric complexes. Okay, so in 2D, let me do it this way. So it's if you're familiar with graphics complex, it's similar to that in that you've pulled out the coordinate points that are there. You can define a bunch of cells, and cells here are things like line, like tetrahedron, like polygon, and so on. But it's required that these cells are disjoint. Okay, so this is actually very hard to use directly, and we don't envision sort of a whole lot of use directly unless you know what you're doing, kind of thing. But what we've done instead is that there's lots of functions that generate these kinds of objects, and you can easily sort of work on them. So we'll see examples of how these get generated. And so here's a sort of a pure 0D mesh region in 2D, pure 1D, pure 2D. Here's a mixed dimension case where the important thing with these guys is to see how they fit together. So cells can't fit together in this way in a complex, in a geometric complex. They have to be along a whole face, and they're all piecewise linear. Similar thing in 3D, they fit together along a whole face. Or not at all. And you can have mixed dimensions. That's very important because one source of geometry, first of all, we don't want to disqualify curves from being geometric objects or surfaces. And secondly, if you think of many things, like graphics is typically, multidimensional at the same time. And increasingly, I think many areas of science will have to do sort of multidimensional things. You have, like in biology, you have sort of lower dimensional connections between regions, like nerves that are connecting. So in more and more areas, this is sort of an important kind of thing. Now, actual solvers might do what I described for integration. It will pick the maximal dimensional component and ignore the lower dimensional things as dust, basically. Okay, so let's do some concrete examples. So here is a set of points, and I define, 2 cells, 2 polygons, and I'm using a multi-polygon notation. So here's one triangle with coordinates 1, 2, 3, and another one with coordinates 2, 4, 3. These regions auto-visualize, so they will automatically display, and I could use that, in fact, as a sort of input. So if I wanted to, let's do that. That works just fine. Well, apparently not. Oh, because Integrate's not happy with that. It should automatically, and Integrate's happy with that right now. Okay. Anyways, So I defined this region. We can all the, some of the properties that we looked at before. It's measure and centroid, and we can use them. Okay, so here's them starting to be more common ways to use them. Probably from from point sets. Let's say I have a point set, and I can generate. This one is unidimensional. It's just 2D, and we know that the maximal sort of number is going to be 4, right? Because it's the rectangle between -1 and 1 in both dimensions. So if I crank that up to 10,000, I should get closer to that 4 number probably, right? Can integrate over them. We can convert from graphics to get one of these regions, okay? And now we can use some of the properties, same properties that we used before. So I can discretize graphics, and graphics is not, the process of rendering graphics is effectively computing a union operation. So we're taking it to mean union when we say that we want geometry from graphics, okay? The actual sort of graphics itself is a covering because it doesn't really do the union operation. Okay, we can generate these guys from these formula regions that you saw, and now these are the kinds of things that our numerical solvers really need. So normally you don't have to explicitly do this at all yourself. You give the region, if you can give the formula region to a numerical function, it needs to discretize. It will discretize according to the constraints given to it. If it needs a finer discretization to be able to satisfy the precision goals and so on, it will do that. And you'll see in some of the other talks, there are many other constraints that can come in how we discretize to best make that solver work. So for instance, in PDEs, we might have interior boundaries that need to be respected. We will have boundary conditions that need to be resolved very precisely and so on. One challenge here is that a lot of the things that you've seen in visualization, like region plot and so on, and contour plot, is just not good enough in order to do high-quality computations on. So we are ending up redoing and improving a lot of that because, like in 2D, we need to resolve corners of regions really well, or finite element is certainly really unhappy. Or in 3D, there might be creases and other sort of discontinuities, and we need to make sure that those get resolved really well. Oops. Um, 3D. Okay, similar thing, Delaunay mesh. And there is an analog. So in this case, when I do Delaunay mesh, same thing, I get a bunch of triangles inside. And I'm not showing that here, but there is another sort of whole language, but I can, so, what? Oh, that was a graphic. Okay. So in this case, I have 100 points, 632 edges, 1,039 faces, and 503 tetrahedra. Okay, so there's lots of functionality like that in addition, which as I said, I'm not quite showing right now. Here's one from 3D graphics. Again, we can use them just like we talked about, sort of using them, whether we want to solve PDEs or integrate or optimize and so on. So here's an example. So I'm taking, the country of France. I'll integrate over it. I'll compute the centroid by its definition. Here's the centroid. I can plot over it happily. Any plot function. I can solve PDEs over it. So here I'm sort of a diffusion here, And you know, here's that kind of result. So the thing is that once you get into this flow of getting regions, the solvers, the flow, all the workflows that we're building for computing with them should be just uniform and very simple. Now, another kind of way of defining a region as sort of a discretized region is to give boundaries. Okay, so we can give, in 2D, we can give a boundary curve, and we can define what's interior to that. All of this works, it goes back to sort of the Jordan-Brouwer theorem, that if it's oriented and it's closed, simple doesn't self-intersect, although that's not needed. There will be one region that's finite and one that's infinite, and we define the finite one. In particular, you can have many of these curves. So you can have holes in region, which our polygons can't do. And how do you know that something is in the region? So it's defined by you taking a point here, where my mouse is. So that point is in the region if you can take a ray to infinity, and that ray is going to cross your boundary an odd number of times. Then it's in the region. So you can have any number of these curves. They can be nested. It doesn't matter. You know, you can have you know. And the same principle goes on for 3D. So you have a closed and oriented surface, okay? And a point is in it if you take a ray to infinity, and that crosses the boundary surface an odd number of times. So here's some things that happen in 3D. So we have a void, like this thing here. If you can see that there's like a little thing in there. A void, you know, that's another closed surface. So if you can see that you set a ray in there, you go to infinity somewhere, and you see that you crosses two surfaces, right? So it's not in. This is not a separate surface. The whole thing, outer surface here, with a tunnel, it's one surface. And you can have any number of these tunnels or handles, depending on who you are. These are often a little bit easier to use for direct definition. But again, it's sort of at the piecewise linear level, so it's quite a lot of detail. So this is the way they're defined. We have a set of points, like we had for mesh region, and then we have a set of curves in 2D, closed curves. And in 3D, we have a set of surfaces, closed and oriented surfaces, any number of them. Probably the most easy way to generate them is by other constructors. So if I have a mesh region, I compute the boundary mesh of it. It will compute one of these representations. Now this kind of representation cannot define lower dimensional things. So it cannot represent a curve in 2D. It cannot represent a surface in 3D, but only solids in 2D and solids in 3D. So when you do that conversion, you'll drop all the lower dimensional things. Both of these discretized forms can only represent bounded regions. The typical case that they're used for is sort of high, like mechanical components and so on, things with high complexity. Oh, okay. Right, so let's do an example. So here is 3 points, and here is a closed curve, you know, 1, 2, 3, 1. That one, the auto-visualization is off right now. It's wrong. It's a bit filled. That's why I wasn't showing it. But that one will also auto-visualize. But I can use it just like any other region. I can integrate on it, you know, and that's the solid. You know, so the area is what I'm computing here. Let's do one with holes. So I have an outer and an inner. So I join these points, and here's my outer curve. And here's my inner curve. Orientation doesn't matter at all, by the way. It's just a ray condition. Okay, and that's the area of that. If I have a set of points, a random set of points, I can compute the convex hull. And the convex hull, it's not just a set. You can get the points out if you want to, but it's important to get how they are connected, the topology. So the convex hull mesh gives you boundary mesh region, which maintains the topology. And now I can use it just like any other region. You know, I could so PDEs over it, integrate over it, optimize over it. we can get it from, so here's when I'm computing it from a mesh region. And again, so I start in some other kind of representation. So we can go, it's not all there now, but we can go from all the representations across. We can't go back to formulas and symbolic ones, but we can go from those to the numeric ones. And we'll increasingly start to get functions that goes to sort of recognize simpler kinds of shape, kind of like a smoothing operation. This is a cluster of points, but I really wanted to recognize a line. It's a cluster of points, but I really wanted to recognize a familiar shape. Okay, here's from polyhedron data. And so I just, in this case, take the coordinates and the faces. So here's an icosahedra. And now it's a region, so I can compute with it, like we do everywhere else. Again, we can do the convex hull mesh from random set of points. This one does not have, if I showed this one, if I show this one, this one auto converts to graphics right now when I use show. But if I set base style, opacity, 0.5 or something like that, you can see that this one does in fact not have any tetrahedra inside of it. It's just a boundary. Okay. Okay, so here's an example piece of geometry in our example data, the Stanford bunny. So I compute the convex hull of that bunny. Then again, it's a region, right? So everything that works for region should work for, however I constructed it. So this is the volume of the convex bunny. All right. There are many more topics. But this is a sort of an early preview of what we have here. And you'll see this afternoon, you'll see other ways to construct regions. We can derive regions from other regions. You've seen a little bit of that here. But we can do Boolean operations on regions. We can transform them or inverse transform them. Both general, nonlinear, and affine, and so on. There's a lot of things to say about data. When you export these, if they're full D, 3D regions, of course, we should be able to 3D print them. We know how to do that. We'll probably provide sort of a data packlet with lots of these formula regions, which are well-known names of curved surfaces and solids. So that's easier. What I didn't show, so there are many things I didn't show. But at the mesh level, this has elements of geometry and elements of graphs, elements of topology. So there's a whole language for setting properties on individual points and edges and faces and so on. Sometimes very important for solvers, or very important for solvers, numerical solvers, but also important for illustrating and understanding these regions. So there's a whole world of that that we'll show at a later date. And that concludes my talk.